Okay. Lots of attention. Uh, what did we discuss so far? Modeling using curves, and then from curves we moved to surfaces. Now we want to talk about other ways to model. Once again, we have an image in mind. We want to tell the computer that the image, the shape mostly, that I have in mind to generate. So we want to to talk about implicit modeling. Yes. The shape. I'll ask for this subset. To whom do I still owe stuff from the midterm? There are a few that I owe things in the midterm, like double checks that some people ask, missed, couldn't wait. You?
So you said, I emailed you about a particular GRC, and then you said you would send me the
okay.
And I don't think you sent it yet.
I did not. So that's one.
What was the question?
Do I owe you stuff for the midterm? Like, there were midterms that I fully graded. There were some that I graded almost fully but had problems with things that were poorly scanned or poorly written. Are you?
No.
Okay. To owe, and yeah. To you, I owe two subsections. Do I owe you pieces about grading the exam, the midterm? Like, to you, I know. Do I owe you? No. I graded all the questions. Okay, perfect. So it's only you and okay. We start modeling. We covered modeling. The idea of modeling, we have a shape in mind. We want to tell the computer that's a shape that you are going to work with. And in the next step, we'll put skeleton and kinematic and inverse kinematic and physics and springs between the things so they can even start to move in a way that we want, namely running animation. At the moment, we just have a shape in mind, like dinosaur or snail, with both examples of both, and we want to tell the computer that's a shape that we have in mind, and it doesn't need to be extremely realistic, quite the opposite. And we want to speak about how do I represent the boundary of the shape. So I have a function, f, and I'll say that the surface happens for all the points p. P is a point in 3D, for which f of p, the level shape, is 0. Desperately needs an example. Sphere are all the points p for which the distance from a point p to the center of the sphere equal minus r squared equal 0. So that would be an implicit representation. And we discovered, by the way, that when we have such an implicit representation, finding where a ray hits it is, at least in this shape, is simple. The same goes for a plane. Again, an implicit representation. The moment that I say, right, f of p is some expression that involves all the points p in 3D, and then I force this expression to be 0, that is the level set to be 0, that would be the value of the scale. Right. And okay. Parametric shape, not discussed today. We have some other value, like for curves it would be time usually, so to describe a point along the curve. So both the x and y coordinates were given by time, and for surfaces we had u and v that placed t1 and t2 two times, because it's two-dimensional parts. Ways that we discussed before, here's implicit representation of array, just to remind us, or an implicit representation of a triangle using barycentric coordinates. Okay, splines and surfaces we already passed. So we can, now when we have the function, which at the moment undoubtedly looks like an unnecessary headache, but when you will see what we are doing with this, I hope that it will make sense. So once we have this function, and keep in mind all this time that the function might be f x, y, z, let's keep this example, is x squared plus y squared plus z squared minus r squared. Z is a function that we might have in mind, and if that's a point 0, 0, 0, then this is just the sphere of radius r. Okay. So in all the cases, the zero set when if x, y, z satisfies f of this equals 0, then that defines the surface for us. And by the way, we can now decide for a point P, is this point P inside or outside the shape? If it's inside the shape, we want f to be smaller than 0. If it's outside, larger than 0. That's just a different way to say there is an inside and outside. Okay. Let me quickly skip to a related topic in computational geometry called alpha shape. It's not exactly in graphics, it mostly comes in shape analysis, but it's extremely useful tool related to study what a set of points of the shape represents. Here it's coming, for example, from computer vision application, if it will ever finish. Oh, we'll return to it. So, yeah, we'll get back to alpha shape. Yeah, implicit shapes, we will see that once I have my shape using implicit representation, let me have a quick promo, show you shapes that I can do with implicit representation. The sphere, or these guys we already know, but with a bit more work. It will mostly be used for blobs, or persons and shapes and trees, and that I can easily control in similar way. So that's where we are going. It's cartoonish, but it can be very detailed cartoonish, especially. I'll show you. Okay, so what other good things do we have is that once we have the shape, it's very easy to control them. You're the animator, you want to move points or to put points on trajectories and change the shape, but we can also do rendering either with Z-buffer or with ray tracing very quickly. We'll have very fast algorithms that tells us where a ray hits the surface. We can quickly find if two shapes intersect each other. That would be if they're pushing, pulling each other, especially if you're talking about animation. But it will be relevant for solid modeling. Again, I want to describe shape. Remember constructive geometry, which covered shapes as union of shapes, or one shape minus another one. That was another method. It will see revisit these topics here of representing shapes as Boolean operations, like take one, intersect with another, union another, subtract another, translate one with respect to another, and so on, will also fit very well for implicit representation of the shape. And it will be easy to simulate, and it will all satisfy what we need from all the modeling. If I want to design the drink, or I want to change very few parameters and generate the rest of the image. I don't want to have billions of triangles that I need manually to change each vertex by itself, right? So I want to be able to control the shape with very few control parameters. Okay, implicit functions, we had it, every function f of x, y, z equals 0. That's implicit. Explicit would be just z equals something of x, y. Z equals square root of x squared plus y squared would be semisphere. And a natural rotation would be maybe distance function would be one way to represent such a shape. So f might be the distance to something in the shape. Sometimes I'll use algebraic equation. Sometimes I'll combine the whole things with voxels, especially for ray tracing application. Voxels with the implicit representation will combine very well. Promo, if you heard about marching cubes, we'll discuss it today. Spheres, once again, coming up with its equation over here, just a small r instead of large r. Various other shapes that are all quadratic or polynomials, everything that you can do using only polynomials of degree 2. But it's polynomials that contains what? You have degree 2 of constant, linear in x, linear in y, linear in z, and then all the combination of x times y, and so on, and all these shapes you can generate in this way. Okay, and when I'm talking about the implicit representation of the shape, we thought about it as f of p or f of x, y, z equals 0. That is, these are the points for which the f equals 0, but it would be convenient for various applications to think that f is actually defined for each and every point on the space. F is defined everywhere. The shape that I have in mind satisfies f equals 0, but there is f everywhere, and actually there is gradient, like force field, that is coming together with the shape. I can think about a shape, if that's a function, then I have gradient that says if you go in this direction, f will increase. On the boundary of the shape, f equals 0, but this is a good direction that you want to go if you want to increase f, which we will use, well, asking. It's convenient to think about it as a force field that repels or contract points into it, but I'll also show you points that's a direction that the function changes the fastest, which we will use for spit it out.
Distance to some point, so if you don't. What collision?
Reflection, shading. I'll need the normals. So being able to compute the normals so easily is one of the good advantages. You know, these change the direction of maximum change is exactly the normal, and I would like to use it. So how can I define the function? I can define the function as the distance to each point. And now I'll say I have 2 points. I'll say I want to compute the distance to each one of them and to create a level shape using this distance. Say the distance to the nearest point, I have my 2 points, A and B, and here are all the points with distance of 1 from A. Here are all the points of distance 1 from B, and the union of both of them, that is for every point Q, my function f of Q would be the distance to the nearest one, the minimum of Q minus A, Q minus B. That's my distance function. If I take f of Q minus 1 equals 0, I'm getting what? The boundary of the union of these two creatures. Do I want to use it to create this shape? Not really. I don't like these points. There are no. I don't have derivative here. It's bulb. It creates these two bulbs, but I want something that will change much nicer when I add the shape together. So Gaussian is a good idea. So first, I will reverse the function, and I will not use function for which f increases when I'm going out. I'll use function that the closest I am, the closest I am, the higher the value. That is, I will not use fi as a distance. I will use fi as 1 over the distance to the point. Why? Because it works, because it looks nice. And even 1 over the distance square will work even better. I'll have an example coming up that will try to convince you. So, and now that's fi, that's the distance to one of the points, and I want to create the level shape of both of them, or I can even use our favorite Gaussians. And now for each and every point, I'll define the Gaussian as the distance from Q to the data point Pi, and the minus here implies that when you're going away from, when Q going away, this function goes down very fast. And at least it's very smooth. Right? You can take its derivative as many times as you want. How does it look, therefore? Does it visually make sense? So here I have one point A over here, and I created the Gaussian of this function. Okay, so that minus the Gaussian, in case you don't remember, e to the minus the distance from the point xy to a square, and the minus here means that it's 1 over e to this one. And the rest is just normalization. I can make it smaller and larger. Now, what would be the boundary of the shape? I'm just in 2D in terms of 3D. I'll just chop it at some particular height, and I'll get a circle that is around A. So now I'm just asking at the contour, the 0 level would be when E equal 1.64. That's a shape that I want to take. But so far I didn't explain everything. I just show you how to create a circle in or a sphere in 3D in a very convoluted way. But what happened, I want a bulbiness in the sense that things should more combine together. The union should be smooth, the intersection should be smooth. So let's add another point, B. Another point, yet another Gaussian just popped up. And now the shape is a combination of these two Gaussians. Here is another one, C. For the point C, again, the Gaussian that is what? Going up. The maximum is obtained exactly at C. How do I create the curves? And that's a point that you need to say, aha, the things that you said make sense. Let's take this shape and cut it. And now you see that I can decide to cut it in different ways, but here is a 0 level and the union of these two. Maybe I can. So now I can take the function S that is a sum of these three guys. S is a sum of these three guys, and now here is a bulbiness that these two guys are creating. Or if I remove C from here, the 2 points, and they're moving very nicely from one shape to another. You can control the parameter where exactly you want the 0 shape, so makes them a bit more separated or a bit less separated, right? But at least, hopefully, I convinced you that having a point, 2 points meeting the union of the 2 shapes is now very smooth and very natural. Make sense to everybody? What, at least, got the point that I'm trying to show? Using distance function as itself will create nasty things even for 2 balls. And where I'm going with these things next is that I have a stick figure that's a skeleton, that's a hand with exactly 2 fingers, and that's a skeleton that I control in its animation, and then I'm adding the skin by creating a surface around it. And what is this surface? I don't want that because I have too many objects here, or I have 3 segments that meet at this point. The summation of this ball should not create a big ball surrounding it. I want a smooth transition, even if there are the summation of a few items, a few segments. And around a single bone, the part that I'm getting is just this one, just elongated. So Gaussians are okay, actually Gaussians are great, except that, what? So I can use the Gaussians, it will create very smooth versions, but it's not local. I'm moving 1 point. It means that no matter how many points I have, I'm summing up all the Gaussians. On one hand, it guarantees that it's very, very smooth. As many, I can take the derivative as many times as I want. On the other hand, but that's easy to solve, changing the point A will change the surface everywhere. I can have plenty of points. Changing each one of them theoretically can change the value everywhere. At least I need to compute the value everywhere to know if it changes or doesn't change. So what we'll do is define that this is a function if we use Gaussians, except that after some distance, it's 0. And then we have some locality. So, make sense? So instead of having fi everywhere, I'll say that if the distance from Q to Pi is larger than some predetermined distance, it's just 0. But, of course, it will break the smoothness around it. Now, since that constructive geometry is in our background all the time, that I want to take unions of 2 shapes or intersections of 2 shapes. So when f is defined in this way, that is f going down or going up, you're going, f is 1 over the distance instead of being the distance directly, you'll see that the union and the intersection are pretty much just the maximum of the 2 functions will give me the, for every point, f, the maximum of f1 of fq equals 0, the 0 set will give me the union of the 2 shapes, and the intersection takes a minimum of f1 and f2, will give me the intersection of these 2 balls. It will be more useful later when we'll get back to constructive geometry. So far we saw Gaussians are better than straight distance. We had 3 options. We had just use a distance, that was a sphere that defines right here, or the square of the distance, or use the function that is 1 over the distance, or 1 over the distance square, that was already better. And we thought, and that was the original function, use the Gaussians instead of inverse the distance. That is nice and pleasing geometrically, but is overkill in terms of the computation power. Okay, so we define the distance, just repeating in this slide. Consider the function f of x is the distance minus r, that's is the first option, and then we improved it by having 1 over the distance, or 1 over the distance square. Okay, more examples all over the web. You find plenty of bulbiness examples and how they behave and how they separate as water drop, which is, if you want, that's great. And so you'll put a few points too close to each other. It doesn't mean that the radius increases ridiculously high, as opposed to the distance. If I take the summation of the distance, even if I have a few points close together, the shape that I get will not be n times larger than the original shape. And they have nice behavior when the 2 points are still close to each other, but not still close to each other. There is a nice transition from one bulb to another. Okay, fall-off filter is a fancy way to just say, if your point is here and your query point is here and your data point is here, then point that is very far away, its f is 0. Don't take f unless it's relevant for the points that you are asking about. Just assume that f is 0, otherwise every data points need to be computed for each one of the points in the geometric scene, which is ridiculous and need to be recomputed the moment that I moved any one of these points. So that just says, decide about a maximum distance, and above this maximum distance, the contribution of pi is 0. Okay, Blim, going back, it's way over 86. That was the Gaussian, the original function. Again, e to the minus distance square. That is 1 over e to the distance square. And what is r here help us to do is some target function which playing with the GeoGebra, playing with what would be for the Gaussians, like standard deviation, will make the bulbs, one of them, smaller or larger than the other. Right? So I can decide that one such bulb is smaller than the other bulb by placing either a constant before the e or changing the r itself. Okay, so that's a blobby model, sum of 4 blobs. So more such images, sum of 2, sum of 60. Start to see the details, see why it's nice. But how many of you worked with this? I think that okay, more than, yeah, quite good, I think, even in this poor quality. Okay, a lot of them. Okay, if you look for Wikipedia and Meatball, you'll get a bit more historical part about these functions that are same idea, just work much faster and not as complicated as the Gaussians. It only said that the distance from a point D would be, I'll decide about a threshold R. If I'm a point and a data point is more than R away from me, then the data point that is more than R away from me has 0 implication on my value. Doesn't affect F at my point. So that would be, if D is larger than R, then G will be 0. Otherwise, I need something that has so the input is go the other way. Yeah, Okay, so turns out that it works with practically these polynomials just do very well. It's not d is yeah. So instead of 1 over d square, it's enough and quicker to compute 1 minus the d square. So we want to have it going down. And simple polynomials, and well, it works. It's like a good example. And why are these strange constants that appeared here and here? It's just because we don't, well, when we are moving from d, from less than r cubed, r over 3, to more than r over 3, we just want the function to be continuous and smooth. So that's why you see that you're getting the same continuous and smooth function when you're moving from one segment to another. Okay, so I'm not going to say much about it. Besides that, it's popular. And and when I mentioned that, ask if you played with it. Yeah.
Do these points like all have their own radius, or is it one radius for every?
I don't know. I don't know, and I got annoyed because I tried to download it today, but it's under Spenger, and decided that I'm not cooperating with the evil empire, so I did not pay yeah, so that's one of the but and where you'll find it is in Blender. That's where I suggested that you might have played with this before. That's I'll show you a YouTube later that gets to the details that walk you through building a model with it. To answer your question, if it's the same R or not, I would think that not. I would think that that's the whole head over here is one sphere versus ear and blobs that are much smaller. So I would think that it's probably right with head as probably one single blob versus the nose, etc. That looks a much smaller blob. So R is much smaller. That would be my intake, and probably each one of them comes up with its own constant that says how influenced it is. Okay, if these polynomials were not complicated enough, here is, you can get away again, a paper that was also protected. Why? Because it works. It's create shapes that are easy to control. That's what I can tell you at the very moment. But you see at each time it's d square over r, it's d to the something over r to the same thing, implying that everything is normalized by r. So as you ask, I can have it smaller or larger, normalize the distance as I'm making r smaller or larger. Okay, and just a comparison that the original Blin the exponent becoming 0 only at infinity, the other one you're chopping up exactly at 1. And hopefully I'll have better answers for next class. And as I said, it's becoming even cooler if I have a stick figure out there that all I control is a skeleton, it is a two-dimensional, the vertices of the skeleton and the skin around it is edited automatically, and I'm avoiding the light, and this is much more challenging in terms of the distance function, because naively adding at each point the contribution of each one of the segments would mean that if I have 3 segments, that means at the interior, at the bone right here, I do not want the bulb around it. If I just sum them up, it would create artificial flatness at places that I don't want. Why you really want to? Why picking these functions in a nice way is non-trivial. Okay, well, picking the wrong parameters would mean that you have the flatness over here. Another example, and again, it's asked to be animated, it asks to be moved. Now, we'll change the skeleton only, for example, put every vertex on a curve, or do reverse kinematics that we'll talk about. And now you can, the whole shape moves. You have the function. Take the function, take its derivative by x, derivative by y, derivative by z. You're getting a vector in 3 dimensions. Where this vector points to, immediately out. Okay, so if you find a point on the surface, you immediately know the normal. So finding the normal, quite nice. It doesn't have to be unit length, so maybe you want to normalize it to make it unit length as well. Okay, and if you don't have the function exactly, then essentially it's easy to approximate the function because you at least have it sampled by pixels. So if I have the function at f of I and j, so if I take f of I j minus 1 minus f of I j plus 1 minus f of I and j minus 1, and take half of both these things, what did I do? It's I approximated the derivative of f of I and j are, say, pixels. So this is an approximation of the derivative of d to the j of this function of I and j. But j plus 1, j minus 1, just discrete evaluation of the function at f. Yeah, so the original video that was referred to in this slide, I was not able to find.
There are businesses whose sales are decreasing, projects are failing, and team collaboration is practically non-existent. And then there are businesses that use Bitrix 24, an online workspace that features over 35 tools for successful sales, marketing, project management, and collaboration. Get it now free at bitrix24.com.
What's at the bottom, I think?
Larger and then Control P. Normally you don't have to worry about
Yes,
the
drag it up, right there, below it, below your mouse, down a little bit,
like
right there,
the paint with
YouTube.
automatic weights,
Right
which
there.
in most cases will give you a kind of decent.
Okay, so out of
everything
all
seems decent.
these,
In this case, it's not.
it's an hour and a half that I found. I don't know if it's exactly the same slide and everything, but it starts by telling you how automatically Blender puts the mesh around it. What I took from this function, what I took from this video and wanted to show you is that I can define the skeleton and has the reverse kinematic of moving the skeleton by itself. And I attach different parts of the skin, the outside neck, to bones that are connected by joints and moving them. Supposedly everything moves. So yeah, that's Blender and that's an hour and a half. And so that's a number of, yeah.
The best way to visualize this, I'm actually
So
going to go into
I assume that there was legal things, so why do you think it's not available? Okay, now we use the implicit function to show our imagination about the shape itself. Now we need to do ray tracing or rasterization. That is, for each ray, you know how to generate the ray. We need to check whether the ray intersects the surface or not. You did it in homework 2 for spheres and billboards. The same goes for all the functions that we had earlier. That's one way to do it, to find exactly where each ray intersected. Okay, but we'll show other tricks. Right, so we don't have triangles that we can raster, at least not immediately, but we'll see ways to generalize triangles out there. So basically have a ray. I want to ask when this ray hits this object, when I know that along this ray, if I'm inside an f of point here, inside f of this point will be less than 0. If I'm outside, f is larger than 0. And I want to find the first point and ignore the issue that I might overshoot. And I don't know to distinguish between this and this. So since f could be as simple as the distance to the function, this would be the distance to the boundary, then I'm looking at the distance along this way, and I'm asking at which point will this distance be 0. But the distance doesn't behave nicely. It doesn't necessarily goes down linearly inside the shape. So I want to find where, as I'm moving along the shape, I look at what is my f value, and I know that when I'm inside the shape, my f will be below 0. Inside the shape meaning f is negative. Outside the shape is positive, meaning that somewhere in between, having f being continuous, somewhere in between there is a root where the two guys intersect each other. So we can do binary search. Or we can do, people ask about Newton-Raphson. So let's talk about Newton-Raphson. So right now, our problem is we have a function, simpler or less simple. At some point, this function, the parabola, should be 0. And I want to, that's the root, and I want to find the root of the function, knowing, or hoping at least, that there is a function that exists. Binary search might be too slow. I want to expedite binary search. So what is sometimes called Newton, sometimes Newton-Raphson? What do they say? You start from some point. It's not binary search, I don't have 2 points, just start from 1 point in my parabola. And I want to pretend that f changes linearly. It's not. That f green is, f is a green, but let's assume that at least I'm close enough to the 0, there are not too many changes, that the function is more or less linear where the root is. It might be true, it might be false, but that's assumption that the method is doing. So if it's linear, what will be the equation of the linear function that is tangent at this point? If it's linear, I'll just compute the derivative. If I start from a point where x equals 3, compute the derivative of f at 3, and say that g of x, which is x minus 3 times f prime, that's just the equation of the linear function that is tangent to f at my starting point. And now ask this linear function, where does it hit the x-axis? Let's compute where does it hit the x-axis. Look at this function, ask if this equals 0, move f prime to the other side. Remember that you're going through f of 3, and it will hit the x-axis set y equals 0, and the x-axis is f of 3 divided by f prime of 3, all of it negative. So that would be my second guess. And hopefully I didn't get far. It can take me away from the root, by the way. So depending on how close to the root I am, it can work or not work. It can actually take me away from the root. But if I start close to the root, then what do? My first point, linear interpolation. Here I am. That's my second point, do the same thing. Third point, do the same thing, linear interpolation from this point. Fourth point, and voila, I'm close enough. So Newton-Raphson is very, very popular, much faster than binary search in most applications. Okay, so back to our algorithm. We have one way to, if I have the force function that I know that is positive as negative, and I know that I'm looking for its root, that's one way to find the root, because x is just the t times that you are moving along the way, you can find it. There is a hack that works very nice if f is actually the distance to the function. For every point x, f is the distance to x. And then there is a different algorithm that asks, remember, all I'm trying to ask is where does a ray hits. I shoot, like in homework 2, I shoot many, many rays. I want to ask where the ray hits my shape. If f happens to be a distance function, then I can do a different trick. I start from some point, somewhere here below, along the way. From this point, I measure the distance to the shape. And the distance to the shape happens to be here, implying that as long as my progress along the ray is not more than the distance to the shape, I did not hit the shape. Distance to the shape is always the distance from here to Phoenix is the distance from here to the nearest house in Phoenix, from every house in Phoenix. What is the distance to me? What is the nearest house to me? That's my distance to Phoenix. Distance from this point to the nearest shape, to nearest point. Okay, that's D1. As long as I'm moving along the way no more than D1, I'm safe. I didn't hit the shape. So that would be my second point. And from now, I'll ask again, what is the distance to the shape? Which will define another sphere, the distance to the nearest point, meaning that move along the ray no more than distance to the nearest point, you're safe. And keep on going. Each time you're safe, each time what you're progressing along the shape is the distance to the nearest, voila, you hit it, you hit the intersection point. Okay, so that's another method to do the ray tracing. Not always working for this F. What next can you do? Let's put a grid, and at least every point, every grid cell knows what is a relevant part of the shape that is this grid cell contains. That's our first thought. That is, I'm putting a uniform size grid cells around the boundary of the shape. And now when I shoot a ray, I first ask what is the first grid cell that my ray hits, and if and now I can ask the shape just near where the ray hits. Does the ray hits actually the shape or not inside this grid cell? Or yes or no, or you're continuing with the ray to the next grid cell, to the next grid cell. Maybe you walk between multiple grid cells. But every grid cell knows locally what happened with the shape. Okay? Every grid cell knows within this grid cell what happened with the shape, and you assume that the grid cell is small enough so the shape doesn't behave too crazily inside every grid cell. These grid cells are small enough. And you don't need to cover the whole space, of course. It's enough to just cover the boundary of the shape. So that starts to be much more practical, because it's much easier for the ray to first find which voxel, which grid cell you hit, and then start your search from this voxel. Reminding, by the way, with some of the methods that we saw for texture mapping, where we combine ray tracing and texture mapping to get, remember, the parallax map or the deformation map. We did ray tracing, but very local ray tracing, just among the surface that we hit. Okay, so moving along this idea of let's use voxels representation, we have various methods that tries to combine voxels with these implicit representations of the voxels. So voxels, just to show, unit size, just extensions of the pixels. And I can have every voxel know if it's relevant for the shape, and if yes, what's relevant. Most relevant pieces of the shape out there. Or I can say, hey, I have a function f of x, y, z, and I have a voxels, well, pixels voxel representation inside it. Let's instead use all the voxels. So everything is full, but I'll pick every voxel. For every voxel, pick the center point, say. The center point, P, compute its value, f of P, and now the whole voxel know what is f of P. In other words, for each point inside the cell, inside the same voxel, if you're asking what is the value of f inside the voxel, you'll say it's f of P. Even though it's not f of P, it's close to f of P, but I moved a bit from f of P, I'll say it is a linear, it is a constant approximation for each and every voxel. Here are the voxels, the f in each voxel. You're asking with array where it is a value of 1. You will continue with array until you're getting to something negative. As long as it's positive, go from one voxel to another. It's just the beginning of the idea, so it's, at least. You can use it, if the voxels are small enough, it's fine. You can just say inside the voxel, f doesn't change dramatically. I'll just call it a constant. But so just analogous to what? Analogous to what you did in homework 1 as a nearest neighbor interpolation. You had a few input pixels, 4 input pixels, but you have an output pixels right here. You ask what is the nearest pixels out of it, which you just didn't know that it's the nearest. You just did the rounding operations. You got the coordinate of this pixel, and that's the values that you return. So that's nearest neighbor interpolation. What's better than nearest neighbor interpolation? Linear interpolation. But so the pixels, the voxels, the pixels, well, it's not a linear, it's not a constant value of f inside it. The value changes linearly inside the pixel, but I can make it changing linearly inside the one-dimensional thing. What do I do when I have when I have two-dimensional thing, 4 corners? It's not linear interpolation. It's
Quadratic.
by linear interpolation. It's by interpolation of. Let's remind you, it was the interpolation of. Here are my a value f at each one of these 4 points, because I'm only in 2D. So I'll value f at each one of these 4 points. Oh, that's the value of the pixels that you are getting in the input image. And now you have a point Q. What would you do? You're doing a linear interpolation between P1 and P2 to get a linear interpolation at Q left. You'll do a linear interpolation between these two values to get linear interpolation in Q right, and on top of it you have another value of interpolation, interpolate between Q left and Q right to get the value exactly at Q. And you can do it with, remember we said another way to get to exactly the same weight is to think about these four rectangles, and the weight of P2 is what is the area of the whole thing in the denominator, and the area of the opposite rectangle. That was bilinear interpolation. But since we are talking about voxels, it's going to be not, and voxels has 8 corners, it's going to be a trilinear interpolation. Exactly the same idea. You have the values at the 8 corners. Now you can approximate the value at each intermediate point based on first do a linear interpolation by x, or then interpolation by y, then interpolation by z. Exactly the same idea. But you can now ask a bit better. I want, based on these functions that I created, I can do the linear interpolation and do the ray tracing, etc. But I approximate the, I want the skin of the surface. Can I use the voxels to generate the skin directly? So, did I miss it? No. So can I use the voxels to generate the surface directly? Remember, I want to have a surface that is where f x, y, z equal 0. What happens if inside the voxel I pretend that the function behaves more or less linearly, at least piecewise linear? How can I do it? Here is my voxel, pixel, and f of this point is 10, minus 10, minus 10, and minus 10. And f, remind you, is continuous. And I'm looking for the curve of f equals 0, of the xyz, for which f equals 0. Do I know exactly where it passes? No. But could it be that somewhere in the world there is a graph of the function of f equals 0, and if this is 10 and this is minus 10, then somewhere between these two guys there should be a piece of this graph, right? A piece of the skin of the shape. Because between 10 and minus 10, there must be a point where f equals 0. Same goes between the 10 and the minus 10 here. So this is yet another point, implying that unless the function is too crazy between these two shapes, at least a first guesstimate about it is that this is a nice linear piece that contains part of the skin of the shape. It's linear versus the actual boundary of the shape that might not be linear, but at least if it's linear, it's not too far away from it. Now, where did I place these 2 points? I'll use linear interpolation to find where is f equals 0. Use linear interpolation between this and this, thus where is f equals 0, between this and this, where f equals 0, and connect them by a segment. So this would be our segment over here. Now, when you're doing the linear interpolation, it's not trilinear, it's linear, it's on the edge only. So I looked at this pixel, looked at this edge of this pixel, asked where is the 0 point on this edge? It was this point. doing the very same gymnastic from this cell, I still look at the very same edge, and the answer would still be the same. That's where the 0 point, implying that this part of the surface will glue to this part of the surface. But because it's along the edge, you're getting the same answer, no matter if you look at this edge from the left or from the right. So you know that there is a piece of the function over here that will continue to a piece of the function, continue to a piece of the function, each time do linear interpolation. So that's going toward, start to be going toward marching cubes. Okay, so at each pixel, just approximate, find if it has one edge that is moving from plus to minus, more than 0, less than 0, then we are in problems, because it means it's a function that we are missing points. The function might do very strange things like intersect only this edge. But as long as we have two edges that one inside, one outside, we connect them. And we'll get a connected curve at the end, nothing with holes inside. And now this will be the beginning of a triangulated mesh that we can now push into the rendering. So the overall picture, we are using a few control points to define an implicit surface. Using this implicit surface, we create the triangulated mesh that our GPU likes to work with. We are not out of the woods yet, but in terms of generating the surface, but at least that's a good start. Just evaluate what is f on the vertices of the voxels. Now, that was for voxels. Just ask inside, outside, and place the boundary inside. And now we can only keep track of the cells that actually intersect the shape. Nobody told us that all the cells must have the same size. Right? It could be voxels, but maybe it's other region. I'll use voxels that are twice as large, because nothing dramatic change over there. In other regions, even voxels that are 4 times as large, which lead us naturally to oct-3. So this representation is very nicely combined with different level of resolution and oct-3 and quad-3s. What are we doing in 3D? Well, now it starts to be a really tedious case analysis, because in 3D we still pick for every edge. A voxel have the voxel itself, region in 3D. It has 6 faces, and it has 12 edges, around 12 edges. I still find for each one of the edges, 12 edges for each one of the edges. If it goes from larger than 0 to smaller than 0, I think that now the surface, it's not a curve anymore, it's a surface that 0 level cuts this edge. So I need to cut the edge somehow, and there are cases at which I have to handle ambiguity, and this ambiguity actually appears even in 2D. Like in this case, I hope that you all agree that since this is negative and this is negative, I don't have any evidence that f crosses this edge. I'm back to 2D. Nor this edge, because it's minus and minus. I definitely have evidence that f crosses this edge and crosses this edge, so it makes sense to glue them. If you wish, Occam razor, that's the simplest explanation over here, even though f might be more complicated. But what should I do? Let's do the same gymnastic. All I convince you is that the f needs to cross this edge and need to cross this edge. So, well, 2 points here and here. But let's now replace this value to be 10 as well. Now, what happens? There is here I'm larger than 0, smaller than 0, so f crosses this edge. F crosses this edge, crosses this edge, and crosses this edge. Cool, I found this crossing point. Now where is the boundary of f? This is an option. Could be that that's a boundary of f inside the shape, but at the same coin, without having more data points, it would be that it's this one. But nothing in this data by itself tells me which of the two configurations will fit this part. And that's even if I have only one intersection of the surface with f, what happened inside f. I am not sure. So there is some ambiguity, and that's why this method of marching cube makes so much noise, that it can give lots of guarantees, even with a lot of ambiguity. And now it starts to be many cases of pluses and minuses of each part, and you're allowing a few, even more than one, but no more than three. As long as I have just one inflection point per edge, I can guarantee that at the end of the day, what do I want? That the skin that I'm generating will be topologically reasonable. You will not have holes. You will not have part of the skin that connects to nothing. That it will close, each part of the skin will enclose a volume without holes there. And that's a nice thing about the marching cube, that it gives a pretty general solution that is pretty robust and obtained very fast, but just constant time per square. Okay, and now, so you generated all the slivers of linear patches out there using the bilinear interpolation. You're getting a few triangles per each one of the cubes, and that's pretty much tells you what to do. So that was a marching cubes. And we'll skip this one. Now, I can generate a set of points from f and from the set of points to generate the skin. Many algorithms, many algorithms, some of them we saw in computational geometry, to generate the skin from sample points. A beautiful part is that we talked about constructive geometry, right? That if I have these shapes, there is this slide that I'm trying to get. If I have this, so lost the slide, that if I have this shape, the minimum and the maximum are useful to denote the intersection and the volume, the intersection of f, the intersection between the two regions and the union, which is great because it leads me to approximate the minimum and the maximum. You can play with it. I'm skipping details, and eventually getting with the same method the staircase by just having a lot of pieces, build unions, you remember constructive solid geometry, and voila, by just rotating, shifting, and union, that could be the result. So I think that that's a good point to stop. Yeah, so covered marching cubes, at least the idea of replacing pieces of f, if you don't know exactly what is f, but we generate a polygonal surface, triangulated mesh from generating f. And why did we start with f to start with? Because it's much easier to change a few control points or to change a few bones, to change a skeleton, especially if you want to make it move in time. It's much easier to control the bones rather than controlling Bezier curves, control points of Bezier curves, and hoping that the Bezier curves and joined to be Bezier surfaces, Bezier bilinear patches, and so on. That requires you to have much finer resolution, which implies that manually you have plenty of things to control. So that's a much nicer, using the skeleton is much nicer much easier to control way to have the control animation of objects. Okay, good point. Thank you.